by looking at graphs from sort of a mathematical, theoretical approach, like because graphs originated in mathematics before computers existed. And then once we have a solid understanding of graphs and their properties, we're going to take a look at how they're used in programming. We're going to build some from scratch, and we're also going to look at a library in Python that is sort of industry standard for when you want to program with graphs in Python. So let's get started. And I think that I just covered the agenda. Yeah, at the end, we're going to take a look at an advanced graph algorithm, which I think was really interesting. And every hour we'll have about a 5 to 10 minute break. And there will also be portions where I give you the opportunity to code in the notebook that hopefully that you downloaded from GitHub. And then we'll come back together and work out the solution as a group. So let's get started. So first off, we will look at graph is a graph. So a graph is just a collection of nodes, also called vertices, and edges. The singular for vertices is vertex. So node 1 is a single node or single vertex. So here in this graph, we have 3 nodes or vertices and 2 edges. So an edge is just something that connects 2 nodes. This is all a graph is from a simple definition perspective. Before getting into the math, it's not too interesting yet. So let's just warm up our brains with a little exercise, and feel free to use the chat here. How many nodes and edges are in each of these graphs? So we have 3 graphs there, 1, 2, 3. And how many nodes are in each graph and how many edges? Please feel free to sound off in the attendee chat. So there are 4 edges in the first graph. Thank you, B. And there are 5 nodes. So 1, 2, 3, 4, 5 nodes or vertices here. 1, 2, 3, 4 edges. In the second graph, there are 4 nodes, yes. And there are also 4 nodes in the last graph. And then as far as edges, in the second graph, there are 1, 2, 3, 4, 5, 6 edges, right? 1, 2, 3, 4, 5, 6. And then there are 0 edges in this last graph here. So in this graph, every node is sort of an island unto itself. That's a legitimate graph. It just happens to be a graph without any edges. That doesn't often occur. But let's say you're modeling a social network, and you have 4 people who've signed up for your website, but none of them have connected with each other. So that might be your social network at the start of building your website. Not common, but totally a legit possibility. So let's move on to the next slide. So there are 2 main categories of graphs: directed graphs and undirected graphs. In a directed graph, edges have a direction, so indicated by this arrow here. So here we see that node 2 is what we call a neighbor of node 3, because node 3 points to node 2. However, node 3 is not a neighbor of node 2. So as far as real life examples goes, if you think of something like Twitter, you can follow people on Twitter. They don't have to follow you back, though. So that is, and also if you're looking at roads, there are roads that only go one way if you are using a graph to model a map of roads. So directed graphs is sort of the first category of, the directed versus undirected, we'll look at undirected in a second, is the sort of big differentiation between types of graphs. It's really important to know if you're dealing with a directed or undirected graph. When you're dealing with graphs in computer science, the vast majority of the time you're going to be dealing with directed graphs. Okay, let's take a look at the next exercise. So which of these graphs are directed? between the first, second, and third, which are directed. So, right, thank you, everyone. The second one is directed because here, as indicated by the arrowheads at the end of the edges. So, for example, this node in the lower left corner points to the node in the upper right, but the opposite is not true. In the first graph, there are no arrowheads, so this is a graphic or pictorial representation of an undirected graph. And this last one is kind of ambiguous because there are no edges. However, right now, we can't really say one way or the other. So there's no good answer for that one, frankly, yet. But we know for sure that this one is directed and this one is undirected. All right, the second big category of graphs after directed and undirected is weighted or not weighted. So here, in weighted graphs, edges have a weight. So there are 1,000,001 different use cases for weighted graphs. One could be, let's say you were modeling a flow network and you were interested in showing how much volume of water or whatever is going through your pipe system can flow from node 1 to node 2. So although here it's undirected, here we can say it has a capacity of 3. You can have 3 liters, let's say, per second, if that's the unit, flowing between node 1 and node 2. Most weighted graphs usually don't have negative numbers. There are times when it occurs, but in most use cases, they're almost always non-negative numbers, often almost always positive, because in most use cases, if there's a 0 weighted edge between two things, it may as well be that there's no edge at all. But it's important to know what the context of graph you're dealing with is, and whether or not, if there are weights, whether or not they can be negative. Most of the time they won't be, but there are some use cases where there are. Weighted graphs won't, there's a question in the chat, shouldn't weighted graphs be directed? Weighted graphs won't always be directed. Sometimes they will be. Let's say, for example, I think in LinkedIn, for example, you can only have 2 people connected, not one following the other. I haven't used LinkedIn in a while, it could be wrong. And you might want to weight the edges if you're trying to analyze the network with how many mutual acquaintances do these people have. So there, person A and person B have the same number of mutual acquaintances as person B and person A. So there, a weighted graph wouldn't be directed. Most of the time, most graphs are directed, but occasionally there are undirected graphs and there can be undirected weighted graphs. So like sort of all 4 categories are possible. And yes, so there's a question about like, if there are directed graphs, if you flip, isn't like forward going in one way kind of the same as negative 4 going the opposite way? A lot of the times, yes. That is used when, again, in flow networks, you can consider, if I can send 4 liters of water from node 1 to node 2, that's kind of like saying I can take away 4 liters of water from node 2 to node 1. Something like that. So all of these things are possible. It really depends on the context. And then, speaking of which, you can have directed weighted graphs. You can have undirected weighted graphs. You can have undirected unweighted graphs. You can have directed unweighted graphs. Any of the 4 possibilities are possible. So, which edge in each of these graphs have the highest weight? Which have the lowest? Feel free to sound off in the chat. Yes, so in that second graph, the highest weight is 17. The lowest weight is -4. In the first graph, the lowest weight is 1. The highest weight is 4. And in graph 3, the lowest and highest weight are all 1, and they all have that weight. So nice job, everyone. All right. So let's go ahead and look at the way we notate graphs in mathematics. So we say that a graph G is an ordered pair VE. Ordered pair just means that you can't flip them around. V is the set of vertices. So the vertices themselves don't have an order. So just as a brief reminder, a set is a data structure that has no order and cannot have duplicates. So you can't have the same node appear more than once. And E is the set of edges. Edges themselves are ordered pairs. So a graph is 2 sets, one of which is just a normal set, the other of which is a set of ordered pairs. And if the pair UV is in the set of edges, then there is an edge from node U to node V. So U and V are each themselves nodes or vertices. Again, as I said before, that's the same as saying V is a neighbor of U. And just some little math knowledge. This is often how the empty set is notated, sort of a 0 with a slash through it. So this is how you would write the empty graph, which is a funky little edge case graph that you usually don't deal with, but is a legitimate graph. So let's take a look at how we would notate an example. So here we say we have just some graph. We have our set of nodes or vertices that we call V, our set of edges that we call E. We see A, B, C as the nodes, so we just write the set A, B, C for the vertices. And then we have this edge, AB, so that appears here, BA, which means that it goes, so there is an edge from A to B and an edge from B to A, and there's an edge from C to B, and that appears here, but note how B to C is not present because this is a directed graph. So let's practice notating these graphs in mathematical notation. So feel free to sound off in the chat, please. Graph. The highest weight is 17. The lowest weight is -4. In the first graph, the lowest weight is 1. The highest weight is 4. And in graph 3, the lowest and highest weight are all 1, and they all have that weight. So nice job, everyone. All right. So let's go ahead and look at the way we notate graphs in mathematics. So we say that a graph G is an ordered pair VE. Ordered pair just means that you can't flip them around. V is the set of vertices. So the vertices themselves don't have an order. So just as a brief reminder, a set is a data structure that has no order and cannot have duplicates. So you can't have the same node appear more than once. And E is the set of edges. Edges themselves are ordered pairs. So a graph is 2 sets, one of which is just a normal set, the other of which is a set of ordered pairs. And if the pair UV is in the set of edges, then there is an edge from node U to node V. So U and V are each themselves nodes or vertices. Again, as I said before, that's the same as saying V is a neighbor of U. And just some little math knowledge. This is often how the empty set is notated, sort of a 0 with a slash through it. So this is how you would write the empty graph, which is a funky little edge case graph that you usually don't deal with, but is a legitimate graph. So let's take a look at how we would notate an example. So here we say we have just some graph. We have our set of nodes or vertices that we call V, our set of edges that we call E. We see A, B, C as the nodes, so we just write the set A, B, C for the vertices. And then we have this edge, AB, so that appears here, BA, which means that it goes, So there is an edge from A to B and an edge from B to A. And there's an edge from C to B, and that appears here. But note how B to C is not present because this is a directed graph. So let's practice notating these graphs in mathematical notation. So feel free to sound off in the chat, please. All right, so I'm seeing some answers come in. So for the first graph, right, we would start by first saying that we have a graph, G, which is equal to the ordered pair of V and E. V would be equal to our set of A, B, C, D, and E. So here, this is kind of badly named. This E is different from the set of edges. Let's call this set of edges E prime, just to differentiate it from the node itself. And then in our set of edges, we actually have to write, we could either state that our graph is undirected, or we would have to write both pairs in order. Let's just state that G is an undirected graph, and then we would have the edges AC. So G is just the name of the graph. I could call it foobar if I wanted to. G is just usually what we call graphs in math because G stands for graph. But I really couldn't name it anything. And then we have AC and BC and DC. If this is undirected, I can put these nodes in any order. And all right, I ran out of drawing room because this program can only take so many doodles at once. But hopefully we get the picture. So, no problem. So I'm not going to bore us all to death by writing out all of these, but hopefully we get the picture. Note that in this second graph, we would have DA as an edge, but not AD, for example. And in this last graph, there are no edges. So there the edges would just be the empty set. All right. And next slide. So if G is an undirected graph and UV is in E, what else must be in E? So if we were to explicitly write all of the connections out, and G is undirected, and UV is in E, what else must be in E? Yes, nice job, JW and OW, and everyone else who's going to put that same answer. Fabulous. VU must also be in E, lowercase v, because capital V is a set of vertices, and lowercase v is a vertex. So because it's undirected, if there is an edge going from U to V, there must also be an edge going from V to U. So basically we're saying if this is in our graph, and it's undirected, then we know there's also a connection going that way. And in an undirected, this is equivalent in an undirected context to just drawing this with one arc. It all means the same thing. Okay, so next slide. Oop, that's not the right button. That's the right button. Okay, so a subgraph is very similar to a notion of a subset. A subset of another set is just a tinier set. And I don't mean in terms of size. Well, I mean that everything, if A is a subset of B, everything in A appears in B. So for example, the even integers is a subset of the integers. Also, every set is a subset of itself, and the set is a subset of all sets. Just some fun math knowledge. So in a subgraph, we basically take a part of our graph. So here, for example, we take our original graph that has nodes A, B, C, and we just take out the nodes A and B. And then we also include the edge from A to B, but we can't include the edge from B to C because C is no longer in our new graph, not in our new subgraph. So the edges that we pick for our subgraph, all of the nodes that appear in those edges must appear in the nodes that we're keeping for our subgraph, right? It wouldn't make sense to have an edge from B to C in this graph because there is no C. So that couldn't appear. That would be nonsense. Okay. So that is subgraph. So a path from U to V is a subgraph where the edges start at U and end at V, and we basically keep all of the nodes that appear in along that path. So, for example, a path from A to B would just be the graph AB that has the edge from A to B. Another path is to A to B to C. Another possible path is A to C to B. Hold on, there's a question in the chat. Weird notation for undirected graphs. OW, it's just depending on the context. If you're saying all graph, as long as it's clear to the reader what kind of graph you're dealing with, then, for example, if you were dealing with directed graphs and there was an arrow from U to V and V to U, you would have to write both. But if you're dealing with undirected graphs, you would usually just write one instead of both. Okay. So that a path is basically just going from one node to another. You can think of it pretty intuitively as a path along edges. You can define it rigorously in terms of a subgraph. And then a cycle is a subgraph that's a cycle. So for any node V, there is a path to V that runs through the whole graph. And in a directed context, there may not always be a cycle, but in an undirected context, you could say there's always a cycle from A to B if there exists an edge from A to B, because there also exists an edge from B to A. So usually when you're considering cycles in an undirected context, you don't really consider the possibility of backtracking because it's kind of like cheating. It's sort of a giveaway cycle. So again, how you think of cycles depends on whether you're dealing with directed or undirected graphs. So let's take a look at some examples. So a little example exercise. Find a subgraph of these graphs that do not have a cycle. So for this kind of problem, identify where the cycles are. And again, it really depends on the context of what you're dealing with. And then see if you can produce a subgraph without one. So each of these are going to have a slightly different answer. I'm curious what you guys have put. You all will put. So I'm seeing in the chat the third does not have a cycle. Correct. So the answer for the third one is any subgraph of that graph, including the whole graph itself, will not have a cycle. Yeah, the second one I'm seeing does have a cycle. And what could we eliminate from that graph such that there is no cycle is the question. So, okay, I'm seeing in the chat that one has no cycle, and I would, for the most part, agree, because to cycle here, you have to backtrack. which you can do because it's an undirected graph, but that's kind of cheating. So I would say that it depends on how you define cycle and whether or not you're allowing backtracking. If you don't allow backtracking, then there is no cycle here. If you do, then you would have to eliminate all edges. So I would say, right, there is no cycle there. And then here in our second graph, we can cycle from A to C to D back to A, or through B back to A, or through B, or we can go C, D, B. So to cut off the cycle here, we basically have to, there are a bunch of options we can do. We can cut off the edge from C to D. And now, if I start at A, I'm stuck at C. If I start at D, I'm stuck at C. If I start at D and go through A, I'm stuck at C again. So we basically just have to cut off the edge from C to D, and then all of a sudden there is no cycling possible. There are other things we could do. We could eliminate all edges, for example. We could eliminate C as a node and all the edges going to and from C. But this is the minimal cut to not allow for cycling. When I say cut, I mean basically snip an edge off of a graph. Okay, let's talk about how graphs are used in the context of programming, because we can write them down mathematically, but how do we actually encode them? So there are two main ways to encode graphs. The first is with an adjacency matrix. So a matrix is, for anyone unfamiliar, a 2D array, basically. So you make bars around the V. Here means the cardinality or size of the set of the vertices. So if you have, let's say, 20 vertices, you would make a 20 by 20 matrix. So, and usually it's referred to, the adjacency matrix is referred to as A, short for adjacency. So for every edge, Vi, Vj, so from the ith node to the jth node, you would set that entry in the 2D array or matrix to 1, and everything else will be set to 0. So for example, here we have an undirected graph, and we see that there is a connection from C to B. So if we go into row C and then look at column B, there's a 1. There's also a 1 in row B, column C. So, and notice how there are 1, 2, 3, 4 edges here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 1, 2, 3, sorry, there are 5 edges and 10 ones. Can anyone tell me why there are 5 edges and 10 ones in this adjacency matrix? Good, because it's undirected. So we only have to draw 5 edges, like we only have to draw 1 edge between A and C to indicate that you can go from A to C or C to A. And so that is why there are twice as many ones in the directed, in the adjacency matrix as there are in the graph drawing. Okay, so let's talk about adjacency matrix properties. If the matrix is symmetric, meaning if we rotate it like this, then we get the exact same matrix back. What does that mean? We just saw an example of a symmetric matrix. So if our matrix is symmetric, what does that mean about our graph? That is undirected. Great job, OW. So, so it's symmetric because if I rotate it and I get the same thing back, that means if I can go from A to B, I can always go from B to A as well. So it's symmetric when it is undirected. What does the diagonal of an adjacency matrix represent? So let's say there's a 1 along the diagonal. What would that mean? And let's take a look back at this slide. So if there were a 1 over here, what would that mean? So the diagonal is just entries along the diagonal. And if I have a 1 in the diagonal, what would that imply? Good. Node to same node, often called a self loop. So that would mean that I have an edge from A to A. In some contexts, it makes sense to allow for these things. Most of the time, it doesn't make sense. But there are graphs in which sometimes we want to know, can something point to itself? Okay, nice job, everyone. And then the nice thing about an adjacency matrix is you can use matrix operations, which we won't go into the detail to here, to do some computations on graphs. So if I multiply a matrix by itself 2 times, I call that squaring a matrix, or we call that squaring a matrix. And that's like, taking it to the 2nd power or exponent. And what that gets us is the ones that occur in that resulting matrix are all of the way, like if there's a 1 there from, let's say, A to C, we can get to A to C in 2 steps. So it shows us all of the paths of size 2 that exist in that matrix. Sorry, that exist in that graph, based on where the ones are in the matrix. So that's a really nice thing about adjacency matrices, that you can use matrix math on them to learn properties about your graph. So